Okay, so let's begin. So, what I want to do is some introduction to graphs. So next week Tuesday, there is a graph theorist who is coming. His name is Nishad Kothari. So I took his advice on what is the minimum necessary needed to understand your talk a little bit. So he told me a few things, and accordingly I'm giving the first lecture. I mean, there are some agenda which I wanted to cover, so it can't be that whatever. But some of the terminology that he wanted me to cover, I'll cover that. So, um, so this is the introduction to graphs, um, and we are going to do a theorem called Hall's theorem. Inig's theorems. So, Koenig, I don't know how to say, Koenig, he wrote the first book on graph theory. And he was a Hungarian mathematician. And in fact, there is a very strong tradition in Hungary of combinatorics, starting with including Erdős, Paul Erdős, amongst Hungarian mathematicians. So, what is a graph? A graph G is a pair okay, a V where V is, I mean, we are usually considering finite set, but of vertices, and E um, is a collection of uh, pairs of vertices called edges. Um, so if E joins U and B, we say um, U and B are in vertices uh, are incident with are adjacent, and we also say that E is incident with U and B. Writing is okay. You can, in principle, you can um, E can uh, um, well, an edge can be between, let's say it. Um, Let me just straight away say this: a loop is an edge uh, joining a vertex with itself. So the picture is as follows: you have some vertices and you have edges which are joining these vertices. So you could have this, could have this. So you could even have edges like this. So this is a loop. These are called parallel edges. Well, these are edges. Well, I should have some kind of more complicated one. Well, this is possible. Okay, so vertices are dots and lines are edges. Um, so vertices are dots, and edges are lines joining them. This is there could be more ways of presenting them. And let's say so we will consider only graphs with finite number of vertices and finite number of edges. So you could have an infinite graph like, you know, all edges, lot of parallel edges coming from the same two vertices. So this we don't want. Okay, and there is a terminology uh, which we use for d of u, or sometimes d of let u1, u2, un be the vertices. Sometimes I'll just write bi for, and this is called the degree of a vertex, ui, um, also called valence of a vertex ui, and it's the number of edges incident with it. And loops are counted twice. Okay, so let's do some common examples of graphs. One is what are called circuits or cycles. So a cycle is something like this. You know, so just one polygonal shape. Uh, these are called circuits or cycles. Then there are complete graphs which are denoted by Kn. So on one vertex, this is it. On two vertex, this is it. On three vertex, this is it. I'll just explain what it is. This is what it is in four vertices. So now you'll get the idea. It's a complete graph is a um, so Kn has n vertices, and all possible pairs are joined by an edge. So K5, so 5. Okay. So you have this edge, you have this edge, and this edge, and this edge, this edge, this and this. Yeah. So K5 has this K5. So there is an exercise uh, that summation di is equal to 2 times the edge center. So the v is equal to u1 to un. So this is in your homework, I think. Then there is a definition. So there are lots of definitions we start with. It's a new topic of a walk. So a walk is a sequence of edges in a graph and represented as, so let's say u0 to u1 to u2 so on. I don't know why I've got v somewhere, and so this is a walk. A path is a walk such that all vertices are distinct except the first and last, except possibly the first and last. So a circuit in a graph or a cycle um, is a path from u0 to u0. Okay, again definition. This is third. This is the second, first, second, third, and then there is connected. A graph is connected if for every pair u v of vertices there is a path from u to v. And a connected component is a maximal connected uh, part of a graph. So just to go back to our guys, this one, these three are connected components. This is a connected component, this is a connected component, this is a connected component, and an isolated vertex is also connected component. So each part you have a path. So if you take two vertices, let's say you take this vertex and this vertex, there is a path going from to here. I mean, there are multiple paths, but still there is one path, right? And I think walk is just, you walk along the thing, and a path is a little bit more specific that you don't repeat it. There's no point going back and forth in a path. I mean, so you want to say a path is of certain length or maximal and all that. If you keep going back and forth along the same line, you get an infinitely long path. So they're trying to avoid that in a path, that all vertices are distinct. So you don't repeat going back and forth. That's the idea for a path, because path is something which we want to use. Walk is something more like a random walk along something, so you can allow repeated entries and so on. So that's a different object that we want to study. Okay, and a simple graph is no loops or parallel edges. So typically theorems are for simple graphs, And let me define a special one, tree, different color. It's a simple connected graph with no uh, cycles is called a tree. So tree, this is a very important object in mathematics, in computer science. Well, I almost made up. Now, if we have any circuit, like if this happens, then it's not a tree. And it's kind of like a, so that's something to understand. The tree is something. So then there are various objects, there are types of trees which we'll be studying. Um, okay, there is a proposition. So the proofs in graph theory are very interesting and clever. Some of them are very easy, but they take getting used to. So today what the theorem I do is extremely clever argument. I mean, in general, it's true for combinatorics that you have clever arguments, but the graph theory is really a. I mean, one reason it hooks you is that it's got really interesting clever. So the proposition is a tree with more than one vertex has to have at least two pendant vertices. And pendant vertices are, so let me color, pendant, pendant, D-A-N-T or D-E-N-T, I'm not so sure. I think D-A-N-T. So, pendant vertex is one with degree 1. So this is a pendant vertex. This is a pendant vertex. So it's left hanging there. This is the internal. So this has degree 1. Okay, and the proof is, so all paths in a tree with n vertices, and we are taking n bigger than equal to 2, are of length less than equal to n, right? So let v1, v2, so on up till vk be the longest path in the tree. Then claim v1 and vk are pendant vertices. Okay, so v1 is connected with v1 is connected with v2 for sure, and then you go on v3 and so on. Right, so there is something like this. This is v2 and so on. This is a path, and we are saying that this one is a pendant vertex. So if suppose V1 is not pendant, that is, it has degree um, greater than equal to 2, then there is a U, uh, a vertex. There is a vertex U such that V1 U is an edge. Right. So if U is not one of V1, V2, Vk, uh, if U is not one, then we have a longer path. Then we have a longer path. So that's impossible. If U is one of V1, V2, Vk, this means there is a cycle. So it's a contradiction. So if this shows that thus U of V1 has to be a pendant vertex. So this similarly, Vk has to be a pendant. A little bit confused about whether it's pendant or pendant. Let me just check online. Hang on.
Professor, I think it's AP and DA and
It's DE or DA?
A for apple.
Oh, yeah, it is pendant. Okay, good. I wanted to confirm because I keep writing it. And I mean, the last time I learned any group graph theory was I don't know where. So I have to at some point tell you about my graph theory professors. I had the uh, most brilliant professor. Anyway, so that proves this. And here's another problem which I will probably give to you. Uh, um, Connected graph. So we will get back to trees. I mean, I'm going to count trees. There are famous theorems and so on. Right now, today, I want to do another theorem. So a connected graph with n vertices is a tree if and only if it has n minus 1 edges. So you can't make a connected tree with n minus 2 edges, for example. And this is very critical to our story. And I mean, once you do your homework problem, this will fall. This can fall. Okay, so what I want to cover today are bipartite graphs, and here V is can be partitioned into two, and there are edges only between V1 and V2. So this vertex set is partitioned. Is called a bipartition of V. So there are two sets, and you only have edges which are over here. This is not allowed. This guy is not allowed. So you only have edges from here to here. So an example is a complete bipartite graph on Mn vertices, where you have m vertices here, n here, and all possible edges. All possible edges. So K33, for example, is a very important graph. There are three here, then so complete bipartite graph on three sets, three vertices, six vertices, three of them. Okay, let A belong to V, and then I'm using this notation gamma A is the set of all edges incident with A. So sometimes I use A, sometimes I use B, depending on which book I'm taking this from. Let A be a subset of V, then gamma of A. Sometimes gamma of A is, in other books, it's written as I of A, incidence. Gamma of A is the union of gamma of A belonging to. So this is all the edges incident with all the vertices of A. So A is a subset of V, the vertex set. Okay, and a matching should write this properly. A matching. There are two. Okay, is a subset E, E1 belonging to E, such that no vertex is more than. So no vertex is incident with more than one edge of E1. So I mean, what we are trying to do is that you have some graph, and you're trying to make some kind of a. So there may be a graph which I'm going to draw in green. You know, maybe this is a graph. These blue things, these guys are all saying, and this is a matching. So each element in the edge set is incident is there's no vertex that is incident with more than two guys, more than one edge in there. Okay, so you can't have this guy, for example, in the matching because this vertex will be too much. So that's a matching, and a complete matching x to y is a matching such that every vertex in X is incident with an edge in E1. Okay, so now x and y, what are x and y? X and y are subsets of um, V. And in fact, this is we are taking V equal to x union y. So this is relevant to a um, so this is restricted. This one is restricted to a bipartite thing. So this matching works for everybody, but I mean one could have. So think of this only for bipartite graphs. So let me just well let V be equal to x union y. I mean well it's not necessary. I mean we'll need we may need so let's right now have this and then we can think of bipartite separately. So let's think of V equal to x union y now, and let x be let's say girls, and let y be boys. Okay, so now I'm coming to the really important part of the
Professor,
course. So
Professor,
yeah,
sorry, my internet was a little off.
I
This
can't
was
hear you. Hang on, I can't hear you, Preeti.
Can you hear me, Professor?
Now it's better, yeah.
Yeah. So I was just asking, like, so in a complete matching, the set Y, can it have more elements than X?
I can't hear you again.
In a complete matching, the set Y, can it have more elements than X?
In a perfect matching,
Professor, he's asking in a complete matching, can the set Y have more elements than the set X?
yes, 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 yes. Yeah. So right now we are only bothered from x to y. So every vertex of x is covered. Okay, so I mean the situation is as follows. You have two sets. Let's say these are girls and these are boys, right? And you could have more than one boy. And let's say these girls are inclined towards or amicable towards these boys. So what one is interested in is some kind of a matching, so that every girl, I mean, you can pair up without there being any, you know, rivalry up. So that is assuming boys have no voice of their own, of course. So it's a unidirectional thing. So what you would like is some kind of a thing that if I take this guy, then this only this chap is um, all this vertex is okay. Uh, this is okay, and this is okay. But now this guy can't get anything because this is already covered, right? Of course, what you could do is you could say, let this be part of the matching. Let this be part of the matching. Let this be part of the matching. And let this be part of the matching. Now, this is a complete matching. So I showed you two matchings. One of them was complete and one of them was not complete. So the complete, non-complete one is this guy, and a complete one is this guy. And of course, this side can have more. So this is X and this is Y. Okay. So well, here there is this, but this is a general theorem. It's not necessary to have it for bipartite graphs. So okay, this is fine. Um, Here I had some extra guys. So necessary and sufficient condition for a complete matching from X to Y is that for every A belonging to X, gamma of A has to be bigger than A. So um, this is known as Hall's marriage theorem, uh, one of the formulations. So the proof is very clever. So this is a central theorem of this is a central theorem of graph theory. And one of the, I would say, uh, yeah, I mean it's one of the fundamental theorems. So it's used all over the place. So first of all, this side, if this happens, if there is a complete matching, that's easy. So if there is a complete matching, then it's clear for any A, gamma A has to be bigger than equal to A. Why? Because whatever the elements of A, that U1, UKB in A, uh, then there is an edge. Since it's a complete matching, there is an edge. U1 V1, U2 V2, so on, UK VK in the matching, right? Because every guy of X is covered. This is part of X. So of course, gamma of A contains V1 to Vn at the very least. Gamma of A is all the vertices uh, which are incident with A. So it contains all of them in any case. So this is okay. This side is easy. So conversely, so this side is okay. Conversely, assume this is the tough part. Gamma of A is bigger than equal to A for every A subset of X. Any questions on the first part or on the statement of the theorem? So let X naught, very constructive proof, let X naught belong to X. Now we have X naughts and not V naughts. Well, doesn't matter. Um, be a vertex in X not incident with the edge, which is not incident with an edge of the match. So, well, hang on. What am I doing? like I started off somewhere else. Okay. So let x be equal to n and let m be less than n and let m be a matching of size n. So we will show a larger matching exists. So larger of course means with more than n edges. Okay, so I mean it's constructive. So you start with something and you say if you have a matching, take some matching. So pick one edge maybe, and then you say if it's not equal to n, then we have to have one bigger one. That's all. Okay, and let all edges in M be colored red. Okay, and the rest be blue. Okay, now let uh, so this blue. Okay, let x naught be a vertex which is in x, which is not in or not incident with anything. Any red edge. That means it's not incident with anything in M. Okay. So we are assuming that M, this small m is less than m. So there must be something in x which is not touching any of the given edges. Okay, and the claim is there is a simple path. Well, for us it's a path, simple path of odd length. So simple simply means uh, path. We don't need this because our paths were all simple. Simple meaning no repeated edges. There's a path of odd length. Okay, it starts with x0. Okay, uses blue and red edges alternately. Okay, and it terminates with a blue edge and a vertex y belonging to capital Y, which is not incident with any edge of m cap. M is the matrix. Okay. So what are we saying? We are saying here is x Here is y. Let's say there are some elements in M which have some matching. So let's say there are some matching here. I should make it bigger. So there is some matching. Let me put it like this. These are red edges. And what he's saying is that there is a path which goes from here, which is blue, which is alternatively blue and red, something like this, and which maybe ends with a Y here, which is not there. So it's an odd length. So it goes once, twice, once, three times, four times, and five times. This is what he's saying. So starts with X0, uses blue and red alternatively, terminates with a blue edge and a vertex Y not incident with any edge of M. So this Y is not hitting anything with M. So if it's done, if so, so if we find such a path, we are done because we can interchange blue and red and get a larger matching. So let me say that there may be some red which is there which is not part of this path. That's okay. What we do is we change the colors of these guys. So we change this and make it blue, make this blue and make these red. So instead of two reds, I've now got three reds. And this one red stays there it is. Is this clear?
Yes, Professor. Professor, just a small clarification.
Yes.
To have a complete matching, don't we need that like the cardinality of y is greater than the cardinality of x, greater than or equal to?
Yeah, so complete, we are just bothered about this guy. Yeah. Sure, I mean, there may be more vertices here, no issues.
I am saying that it's not possible to have less vertices in the other
No, no,
set.
no, no.
Otherwise,
Hang on. No, this is fine. I mean, whatever I've done is fine. I may have less or more. Who's called? Yeah, yeah. Okay, I understand what you're saying. I mean, there is an edge from every guy here to y. So y has to be bigger than equal to x. Yeah. Is that what you're saying?
yes, Professor.
Yeah, yeah. So this picture, I'm just trying to explain the paths. There may be more vertices and so on. There may be more red vertices and red paths and so on. There may be more here. I'm just trying to explain that once you have such a path, then you can sort of flip it and get a better path. Right? Okay, so
Yes.
we want to prove our claim now. So proof of the claim. So first of all, since gamma of x naught is bigger than equal to 1, uh, right? Uh, there is a vertex y1 um, which is adjacent to right? So now this y1, so from x naught we get a y1. Now if y1 is not part of a red uh, edge, then we are done. So we have found a path. It's a odd length part which terminates with a, it alternates blue and red. Well, there's no red, there's just blue. It starts with x naught, terminates with a blue edge and a vertex y which is not incident with any edge of. So this is, so we are done. If this happens, if however, if yi y1 is incident with a red edge, right? Then there is an x1 in x such that, so so that x1 y1 is a red edge. Yeah, so all we have is there is an x1 here and this guy is a red edge. Again, x0 x1 gamma of this is bigger than equal to 2 because there are, by the all by this condition, right? So there is a y2 in y such that x1 y1 x1 y2 is an edge, right? So it can't be a red edge. It can't be a red edge because it's a matching, so it can't come in two edges. Is an edge as a blue edge, right? Again, y2 is either incident with the red edge or not. So I mean, this is true, and again, either it stops or there is a red edge. Either there is a red edge or it stops. So there is something here, then you get an x. So I mean, basically, uh, what we are what we are saying is that you continue by induction. And now I'll write the formal document. Suppose x0, x1, xk, and y1, yk have been determined. Sorry, what's the question? Say that, let me just check. What are you saying? Can y2 be incident on x0 instead of x1? You mean this guy? Yeah, I guess we need to assume bipartite. Yeah, it's a good question. I think we need to assume it's, I mean, it's all the way, it's true for bipartite graphs. So let's do that right now. I'll confirm this at some point. So it's bipartite. Because I mean this inter whatever of, so I'll confirm this, but I think yeah, it's bipartite. So it's a good question. I think everything that what we are doing from here onwards is about bipartite. But this is sort of confusing me that why didn't they state this over here? So I think it's for bipartite. So let's take V equal to X union Y, and I'll confirm this at a later stage. Okay, so
So, I am a bit unclear about why there has to exist a y2 and y. Like, because if we have cardinality of lambda x naught comma x1 greater than or equal to 2, then our two edges, like the two edges that we can take is x naught y1 and x1 y1, right? Like, we don't need a y2.
no, no, no. This is yeah. The this is the okay. What you're saying is, are you saying that my definition of, maybe my definition, okay, let me check this. Maybe my definition, this was edges or this was weights. So uh, as far as I know, this is the edges. I think maybe the definition of this thing is itself wrong. Hang on, let me bring out the book. If I can find it. Maybe it is.
Professor?
Hang on, wait for a sec. Let me go and see if I can find it. It's now we found. Ah, let me check with this guy. Maybe gamma of A is number of vertices rather than um, this guy. Problem is I'm using two different books for two different definitions, and that is confusing me a bit. Yeah, I think that's right. He doesn't say. Says denote by gamma A something, but he doesn't say what is gamma. Yeah, I think what you're right. Ayush, this is the issue. So let's make, because this seems to be the definition should be vertices here. This should be vertices. But that's not true. Hang on. I mean, it's obvious we want vertices, right? We want girls to write more than one boy. This won't work. So edges don't matter, it's the vertices that matter. So I think, yeah, you're right. This must be the vertices. I should remember to check all the definitions very carefully. So, so this is not incidence, that's why it's not using gamma. Okay, so let's go back. I think it's, yeah, so, yeah, what was the question? I've forgotten it either, but I think the resolution is that, um, so his question was that why can't we, if it's edges that we are bothered about, then uh, these are two edges, x1, y1 and x0, y1. Why should there be another guy? So really, I mean, the question is that this gamma should be actually set of vertices, and I think he requires bipartite too, which he doesn't make clear. So I didn't write that, but I think bipartite is also required. So in this theorem, this is for a bipartite graph.
Yes, sir.
This is for a bipartite graph.
So,
Yeah,
Professor,
I can't hear
so
you.
how would bipartite fix the issue? So how would bipartite
Your
fix the
voice
issue?
not coming through. I can't hear you.
Oh, Professor, he put it on the text. He says, "How would bipartite fix the issue?"
No, bipartite doesn't fix the issue. Bipartite is something I think is required in the thing which he hasn't mentioned, the book. What is fixing the issue is the fact that its gamma A is bigger than equal to A. So gamma of A is a set of vertices which have a incidences. So bipartite would mean that they are all in this part. I mean, this feature of alternating paths happens only in bipartite, guys. You have to have all edges going from here to here, and then it will work. So if we go through this again, maybe with a different colored with this guy. If we start with one guy, there's a vertex y1. So now I'm clearly saying that gamma of x naught is a set of vertices on the other side, which is adjacent to x0. So there is a vertex y1. If y1 is not part of a blue edge, red edge, then we are done. If it is incident, then we go to x1 So it is part. So if there's an x1 there, so you get this. This is clear. Now x0, x1, there are two of them, at least two vertices in y, capital Y, which are incident with these. So we find a y2. And again, it's not part of the matching because matching can only have one guy over here. So there has to be something else. So it's a blue edge, and now it works. So I think it gets resolved. And bipartite is needed. I think it's needed because we need the edge to go to the other guy. Otherwise, you could get confused over here. That how do we know that x naught is also not part of this gamma x and so on. Okay, so
Professor,
yeah,
I didn't get why y2 can still not be incident on x1.
I still can't hear you.
I put it in the message, Professor, the chat.
Okay, only y2 can still be incident on x0. Yeah, there's no problem with that. It could be, but we know that this edge is blue. So it could be. That doesn't stop the process. So the point is that if even if it comes over here and goes back, it's okay. We can just change things. This is not a problem. Uh, so let's that won't be a problem. So anyway, suppose this has been determined. Again, gamma of x0 xk has to be bigger than equal to k plus 1. So there's something other than these guys. So there is a yk plus 1 which we get. And again, if it's not incident with the red, then we stop. And if it is incident, then we continue. Otherwise, continue.
Professor, am I audible now?
Yeah, yeah.
So, Professor, I was asking that. So we just knew that x1 and x0 and x1, uh, they must be connected to two elements y1 and y2, right? But
Right.
I'm not sure why x1 needs to be connected to y2. Like the y2 can be connected to x0, like y1 and y2 can both just be connected to x0, and they can still satisfy the marriage condition.
Well, yeah, actually, there shouldn't be a problem too. So what you're saying is, suppose x0 is connected to y1, and then there is a red edge, x1, and then you're saying there's a blue edge. You mean here?
Yeah, Professor, from x0 to y2. And Professor, how are you sure that it has to be blue? Because y2 can be, yeah, this has to be blue. Yeah, yeah. Sorry, sorry, sorry.
I mean, there has to be something other than this guy.
Yeah.
So what we want to show is that there is something other than this guy, right? I mean, other than what is already been covered, is it?
So, Professor, we want a blue edge from x1 to another uh, y, which is in the matching.
So if there was a blue edge here, and you're saying there is no red thing over here, okay, now you have successfully confused me, which is not difficult task, but anyway, let me see. So what we are saying is, um, the simple path starts with x0, uses blue and red edges alternatively, terminates with a blue edge and a vertex y not incident with any edge one. So we want some other incident. So we can't, you're saying we can't demand that this new edge, new vertex be incident with x1.
So, Professor,
Yeah.
if y2 like x naught y2 is the blue edge, then we can just add the x naught y2 edge into our previous matching, right, and extend the matching.
No, I mean, yeah, I mean, we could just replace this guy with this guy.
No, as in our task is to find a matching which is bigger, right, bigger than the previous one.
Yeah.
So if we just let everything else remain the same and color x naught y2 as red, then that becomes the bigger matching, right?
Yeah, actually, I don't think there is a problem with this. So let's suppose this is true, and let's go up and let's stop somewhere. Let's do. Suppose this is true. Over here, you get x2. So this comes to. I mean, hang on. Right? Suppose this happens, and then we have y3 here. It doesn't matter. Maybe it is one. We call x0 is also equal to x2. Let's say this is what you're saying, right? So there's a path like this, and then this also happens. Then once we got x, okay, hang on. I'm not doing it correctly. Okay, let's start with x0 here. Then we get a y1 here. Then we get a red path here, let's say x1. And then you say that there is a blue path, there's a y2 here, right? And then let's say there is a red path x1, x2 here, and then there is a blue path, right? Let's assume this is it, and it stops, right? Then this, and this is a path with two blue and one red, and I can replace this red with this path. What's the problem with these two things? And we are done. You see what I'm saying, Preetham?
Yeah, Professor, Y3 can again be connected to X0, right?
Your mic is gone for a toss. I'm saying let us continue. It doesn't matter if this is it comes back to x0, it goes back. The point is there is a path. Each time we have when we get back here. So what we are saying is that x0 is no. That's the problem because if we have x0, then we don't know whether there is an additional guy. So then we have to sort of delete y1 because we need this condition to hold. Hmm. So let's take this forward till it uh, terminates. Suppose we say that we want x to be different. I mean, I think the issue would be that we'll have to then reverse this then. Maybe this proof can be fixed or something. Okay, so let's stop here then, and let me get back to you on this proof. So let me revert further. I mean, there are million proofs of the same result with a better proof or a correct proof. Let me fix it. Let me figure out what's wrong. Okay, so sorry about that. Uh, we'll leave it as a pending agenda. I mean, if this is true, if we can prove it, then it's okay. If there is a path, if there is some subtlety which I'm missing.
Professor, can you scroll up to the diagram, please? Yeah. Here, Professor, if like say y2, say in this case, say y2 is not connected to any other red edge, right? So
Yeah,
y2 x3 does not exist. In that case, we can just take the previous matching, the red matching, and add the graph x naught y2, add
right,
the
right.
line, add the edge x naught y2, and that will give us the required condition,
Yeah. No, the
right? And
problem is that we have to keep deleting the YKs, right? So somewhere the proof has to take into account that we are getting different ones. So if I think what Preetham's point is that if it comes back to x0, then we have to get rid of this chap,
why, Professor?
because then where are we? I mean, suppose we are at this point. Then we have a
Yeah.
x1 x0 and we have a y2 y1, and uh, this number, well, it is bigger than equal to this, but we need an additional third guy.
Why do we need the third guy if that happens?
I mean, we have to stop at the blue edge somewhere. So that's why we
Yeah,
are
no.
adding
So
the.
if x naught y2 is a blue edge, then that is our required blue path, right? Then we can just completely ignore the x naught y1 path.
Yeah, but I mean, that's not a proof, right? I mean, it should be watertight in some sense. That I shouldn't. So this is like some gochiwazi we are doing, right? I don't know what has happened at the past. Then I have to go back and change the whole algorithm. That means this proof is somewhere faulty, right? I mean, I have to somehow show that yk plus 1 is different from the, I mean, it's connected to xk somehow. That is the key issue. But that's not, I don't think that is required. So there is something which I'm missing, which I haven't, figured out.
Also, Professor, what I think what Ayush is saying won't work if y2 is connected to another red edge. Like if y2 is a part of the matching already, then Then we
We can
can't
still
just add
improve
a
things.
edge from X.
Yeah, so I mean, ultimately, if we have a path, even if it goes here and there, if it's an alternating path somehow, but hang on, so it's not an alternating path, right? I mean, because it's not starting with a blue edge. If you just stop here, it's not an alternating path starting with a blue edge. So there is something which I'm missing.
Professor, but then x naught y1, x naught y2 is the alternating path starting with a blue edge, right?
Yeah. But see, there is something missing, right? I mean, if we are writing this algorithm to get it, it should be watertight. I mean, I should have, or the author should have said, "Ki, do this over here," you know. So I think the objection which we have got is it needs some extra information, right?
Okay.
So let me do some more research and get back. So anyway, there's 1 minute, so I should tell you about my graph theory professor. So so this is exactly what used to happen in his class every day, actually. So I mean, he's a lot more brilliant than I am, but his name is Robertson, Neil Robertson, and he's one of the people uh, who actually proved the four-color theorem. Uh, I mean, Apple and Haken supposedly proved it, but there were issues in their proof. So Neil Robertson used to give a talk, explain graph theory, and after a while he would get confused, and we will all get confused, like you are getting confused, and I'm getting confused, and then we'll get nowhere in the class, and that happened like repeatedly actually. So I hope it won't happen repeatedly with me, but this is exactly what happened to me many years ago. But this theorem actually somebody else had done it with me. So this proof looked pretty much, when I looked at the proof, it seemed pretty easy to me because I had done this proof long back. So this proof was done with Dijen Ray Chaudhary. But let me figure it out. Let me get back to you next time. Let's go over this again. Maybe I was a bit in a hurry to prepare and I didn't go through the thing. So anyway, thanks a lot for pointing out the gaps. Hopefully next time it will be a little better.